Good. Welcome to our series of lectures on special theory relativity. Earlier we have found that the null result obtained by Michelson-Morley experiment, that is the Michelson-Morley experiment experimentally disproved the idea of ether. It means now the light travels without any medium. Then Einstein proposed two theories, that number one, that since the space is isotropic and uniform, the physical laws must be same for all reference frames, whether moving or rest frame, or moving relative to one frame moving, or frames moving relative to each other, but the laws of physics must be the same in all reference frames. And the second theory was that the speed of light must remain constant, is constant for all reference frames. In the last class we worked out the transformation from one reference frame to the another reference frame, which are in relative motion with each other, and we found the Lorentz transformation. The Lorentz transformation means the transformation relation which relates the coordinates and time from one reference frame to that another reference frame. So we have found that if the two frames are, suppose the observer in this frame, for him this frame is at rest, because the observer, for the observer this one is at rest, so this is at rest. Suppose the observer is here, so for him this is rest, and this one is moving with say velocity v. The coordinates which is measured for a particle, the coordinates and time which is measured here is x dash, y dash, z dash, d dash, and the coordinate of the same point measured with respect to the s frame, which is say x, y, z, and we can find a transformation relation between these two, and this is called the Lorentz transformation, which we have worked out earlier. That is x is equal to x dash plus vt 1 minus v square by c square, where v is the speed of this reference frame relative to this one. And since the motion is along the x-axis, v is along x-axis, y and z components are related same. So y dash is equal to y, z dash equal to z dash, and t is equal to t dash plus v x by c square, 1 minus v square by c square. Or in inverse transformation, this will x dash, this will be minus, t dash will be t, here it will be minus, this inverse transformation. This we have already worked out, so we are not going to be interested in this. We are just to recall that what we have done. So now we will do the consequences of the Lorentz transformation. What are the consequences? Because these transformation relation has certain consequences. So the one of the consequences is called length contraction. Length suppose we have a frame of reference which is supposed to be at rest relative to the reference to the observer. Say it is x, y frame, s frame, and assume that a rod is kept here in this reference frame, and the coordinates, x coordinates of the ends of this rod is say x1, this is x2. So the ends the length of this rod will be x2 minus x1, that is say L naught. Now an observer which is moving relative to this reference frame, the observer is here, and this observer has measured its length L naught, which is the difference between the coordinates x2 minus x1, and say another reference frame x dash, and the observer and an observer in s dash moving frame when sees this rod, he measures the length x2 dash minus x1 dash. So the length measured in this reference frame L naught is equal to x2 minus x1, and relative to the moving frame he measures it at x1 naught and x2 naught and x1 naught. For him this coordinate is x2 dash and this coordinate is x1 dash. Now we want to correlate between these lengths. Since we know that x1 for our Lorentz transformation x2 or x1 will be equal to x1 dash plus vt 1 minus d square by c square, and x2 is equal to x2 dash plus vt 1 minus d square by c square. Now we want to substitute, if you substitute these values here, okay, so if you substitute these values here, L naught x2 is x2 dash this, so this is x2 dash plus vt 1 minus d square by c square minus x1. The x1 is this quantity. So x1 dash plus vt 1 minus d square by c square. Since the denominator is same, so subtraction will be, the result will be 1 minus d square by c square. Numerator will be simply algebraically added. So vt and vt will cancel out. Oh, sorry, it's vt dash. Yes. Vt dash is result in this. So vt dash dash cancels out, and we are left with x2 dash minus x1 dash. And x2 dash minus x1 dash is L, the length measured by an observer which is in the moving frame. So this is L is equal to L by 1 minus d square by c square. So from this relation, L is less than L naught. Obviously, from this relation we get L is less than L naught, because this is less than 1. Divide by 1 lesser quantity, so L is less than L naught, and L will be L naught. L will be L naught only when this quantity is 0. So L will be equal to L naught when the length of the rod measured in both reference frame will be same only when V by C is negligibly small, it tends to 0, then it will be 0. So L will be L naught. Or we can say that V is very much less than C. The moving velocity of the moving reference frame is very much less than C, then this value will be 0, because this is very high. This is 3 lakh kilometer per second, and this is a velocity, suppose 100 kilometer or whatever it is. It's very high, so it will become 0. That's why we in our daily life we don't see any length contraction. This result is simply a length contraction, means the length which is measured from here will be lesser than that which is measured here. A moving observer will see the same length of the same rod shortened by this much quantity. So the length observed by a moving observer will be shortened than its proper length, and this observation is this contraction is reciprocal. I mean, suppose if you put this rod in this reference frame, for this observer the rod will be L naught, but relative to this observer this frame is moving, because if the observer in this frame, he supposes himself to be at rest and measures the length to be L naught, but relative to this observer this frame is moving, and the observer in this frame will observe the same length contraction. So this is reciprocal, either of the two, whether the rod is kept in whichever frame has a certain length, the observer which is in another frame which is moving will observe the same rod to be shortened. This is one of the consequences of the Lorentz transformation. And this contraction will be more if this as V increases, the length will be still more shortened. If we take V equal to C, then L will be, this quantity L naught will be infinite, because if we say if V is equal to C, then L naught is equal to L by 0, which is infinite. It means this will be infinitesimally small. If this rod has a 1 meter length, this has a point measured related to the moving frame. If the rest frame observer length to be 1 meter, and the reference frame which is moving with the speed of light will observe the same rod to be 1 point, because this will be infinitely long. It means this is finitely small. So this is called the length contraction. Now the next consequences of this lossless transformation is which is called as time dilation. Time dilation. Now again, suppose we have two reference frames. Suppose this is S frame in which the observer is sitting. Observer is placed in S frame. For him, this observer, this is at rest. And this, according to, related to this frame, this S dash is moving with, say, certain velocity. If this observer would have been in this frame reference, for him this will be at rest and this will be moving. But now suppose we have this, assume that the observer is in S frame. For him this is at rest and this one is moving. Now he measures the two events. He measures the two events. Both measures the two events in this frame, also in this frame. And he measures the two events occur in a time with a time difference of, say, delta t. Suppose the observer in S frame observes two events at a time difference of say delta t. Delta t means t2 minus t. He occurs that he found that the two events occurs at difference when first event occur at t1 and the second events occur at t2. The time difference between the two is t2 minus t1, which is recorded as t. So, suppose he found the star, or say star or whatever. Sees two star. Yes, he sees that you observe that one star has risen at a time t1 and not at the time t1, and the same star sets at time t2, and the time difference is recorded as t2 minus t1. Setting and rising of the star, time difference. The observer in this frame again also sees the same star, and the time difference he recorded as t2 dash minus t1 dash. So for time difference for the same the time difference measured by the observer in S dash frame for the same two events, for the same say he has measured as t dash is equal to dash minus t dash. Now you want to find a relationship between these two events, two time differences. And we have the Lorentz transformation. And the Lorentz transformation is given by Lorentz for time. The Lorentz transformation was that T1 is equal to T1 dash plus Vx by c square. And T2 is equal to T2 dash plus Vx dash by c square minus v square by c square. Now substitute these Lorentz transformation values here. So this delta t using Lorentz transformation. Instead of T2 we have in terms of dash, so it is T2 dash plus Vx dash by c square 1 minus v square by c square minus T1. T1 is T1 dash plus Vx by c square 1 minus v square by c square. Okay. Now here, since the denominator is same, the numerator will be simply algebraically added. So in that case, this term and this term will cancel out. So delta t will be T2 dash minus T1 dash. Minus v square by c square. And T2 dash minus T1 dash is obviously delta t is greater than delta t dash. That is, since 1 by 1 minus v square by c square is greater than 1. So this quantity is greater than 1. So what does this mean? This means that the time is dilated. This means that the time measured by moving frame is, so thus the time interval delta t dash that is the time between two reference frames are the for the same two events are not the same, but time is different. In our non-relativistic case, we assume that time must be the same. The time will be same only when this quantity is 0. It means when B is very much less than C, this comes to up to be 0, negligibly small, then T will be T dash. In our daily life, we have the time is same because our reference frame which is moving or at rest, whatever, if it is rest then it is already 0. If it's moving, then this value is still 0 because C is very high. But if C is comparable to the speed of light, then this happens. Thus the time difference, time interval delta T dash between two events at a point at in S frame S dash frame appears to be longer or dilated by a factor by 1 minus V square by C square to the observer. In the stationary frame, in the means if the time in the stationary frame is say 1 second, then the time that the same event will be measured in this frame will be lot longer than 1. So these are two consequences. There is one more consequence of that, and that is called simultaneity. Although these consequences appears to be funny because we are not accustomed to this type of transformation, we suppose that how a length can be shortened and how the time can be dilated, but experimentally it is proved. So there is no question of its verification, whether it's true or not. We will do an experiment and show that how the time dilation is experimentally proved. But this appears only when the relative motion between the two frames is very high. In our daily life, we don't feel those type of, because in that case, the speed of the relative motion between the two, relative velocity between the two frames are negligibly small as compared to the speed of light, and in that case, there is no light time dilation or length contraction. Now the third is simultaneity. Simultaneity means the two events, if the two events occur to be simultaneous in one frame, it may not be simultaneous in another reference frames. by the simultaneity. That is at the same time, same point time. Means that suppose there is a length in between A and B. B coordinate is x2 here, x1 is here, and P is the middle point. And we flash a light here. The light will reach both at x2 and x1 at the same time, because this is the middle point. The speed of light is same in all directions, so the time taken by the light to travel from P to B will be the same as the time taken from the point P to A. So the arrival of the light pulse at A and B will be simultaneous. Okay. Now if the two events have, this is S reference frame. Observer is here, and he found that the flashes of light reached at A and B at the same time. But now the same thing is being observed by a moving frame with velocity v. What will we see? We will find that there is a time difference between the arrival of the signal at A and B, because still it is moving. So For suppose the time taken for the light to reach to B is t, and that to reach from P to A is also t, same time. But now the time which is observed from here, we say it is t2 dash and t1 dash. So the time same time, say this time is say 2. At the same time, now the time of arrival of the signal at B and A observed relative to this frame, the time of arrival of the signals at A and B relative to S dash frame. S dash frame is moving frame. Will be T1 dash T minus Vx1 by C square 1 minus V square by C square using the Lorentz transformation. This is the position x1 and the time for T2 is equal to T minus Vx2 by C square 1 minus V square by C square. So the time difference here was 0 because the same time, but here the time will be difference will be T2 dash minus T1 dash. So the time difference T2 dash minus T1 dash is equal to T minus Vx2 by C square 1 minus V square by C square minus T in this case there was no time difference, both occur simultaneous, the time here and t is same, so the difference is t0, but here the difference is not 0. It means this for this reference frame the events are not simultaneous. Vx V by C x2 minus x1 or x1 minus x2 1 minus V square by C square. So So this is obviously not simultaneous. This will be simultaneous only when this will be 0. Then T2 dash will be equal to T2 dash, T1 dash. The interval depends on, no, it depends only the time difference. Difference appears between the difference in position and the velocity of the reference frame. The simultaneously, as x2 minus x1 come closer, then only be 0. And or v is if these 2 points come closer, means at the same point, then there will be no time difference only. Or if there is a velocity is very much less than c, then only then v by c tends to 0, then only t2 dash minus t1 dash. It means if the two events which are measured simultaneously in one reference frame, that appears to be at different times in another reference frame. It means they are not simultaneous in both the frames. So we will do one verification. We have one experiment for time dilation. And that experiment is performed, and that experiment proves the veracity of this Lorentz transformation. So verification of time dilation. Verification of time dilation. Obviously, this can be verified only when the observer is moving at a speed which is closer to the speed of light. And we know in the atomic nucleus we found, we know that in the atomic nucleus we have two types of particles, say neutron and proton, but they are not, they are the two states of a single, they are two states of the same particle, they are not different particles. Neutron does not remain always neutron, this does not remain always proton. This is not fixed, but they swap their states. They are two states of the same particle. So neutron converts into proton with the emission of an electron and a particle called electron neutrino. Anti, this bar means anti. So neutron changes into proton by the emission of an electron, and these processes occur in the nucleus because neutron changes to proton, and the reverse reaction is proton changes into neutron with the emission of positron, positive charge, and electron neutrino. So this is an electron neutrino, and experimentally it is found that these electron neutrino are kind of meson. Oh, no, but we are not required here. This is true, whatever I have written, but in this experiment, here we are not discussing those things. In the outer atmosphere, we know that the Earth is showered by charged particles from outside, and these charged particles interact with the atmospheric sphere, and a particle called mu meson is created at that outer surface, outer region of our space. And this is 200, this mu meson, it's a particle which is massive than the electron, and its mass is 215 times the mass of electron, the mass of heavy particle. And this mu mesons decays into an electron, and neutrinos, this decays into an electron and neutrinos, that we electrons, neutrinos which we have just created. And the lifetime of this particle is 2.26 into 10 to the power minus 6 seconds. Means it is created and decays within this very short time. And its speed is, and it has a velocity, this neutrino meson is moving with certain velocity, and this velocity is 0.998, the speed of light, 9.998 times the speed of light. So if we calculate the distance up to which this particle must have traveled, and suppose velocity is this much and the time for it is this much. So if you multiply, we will find that how much distance you must have traveled. So distance is equal to S is equal to Vt. So V is 0.998 times the speed of light, and the time up to which its lifetime is 2.26 to the power minus 6 seconds. If you multiply it, you will get 658.68 meter. But in this up to this length travel, after traveling of this much length, the particle will disintegrate into this mu meson, will disintegrate into electron and neutrinos. And this is very small length. It's less than 700 meter. But we still found the mu meson at the surface of the Earth, which is about 10 kilometer. How is it possible that mu mesons, which are created 10 kilometer above the surface of the Earth, is found here, where it should have disintegrated in this length after traveling this much length? Because we are taking its velocity, it's moving with this much velocity, and the time of it has lifetime is this much. So in this time it must disintegrate here only. But still we found at 10 kilometers at the surface of the Earth. Because we haven't taken into account the time dilation. Because this time 2.26 to the power minus 6 second, its time in its reference frame, and which is moving frame. And according to the Lorentz transformation, the time in which we measure must be different. So that if we take into account the time dilation, we take into account the time dilation. So if we take into account the time dilation, that is time which we have the rest frame is moving, will be longer than the time which is measured in its frame. So it will be delta t dash will be delta t by 1 minus v square by c square. And the time which is measured in its reference frame is 2.26 into 10 to the power minus 6 seconds. And this is 1 minus v square. V is, its velocity is 0.998 c. 0.998 times c divided by c this is whole square. So c square will cancel out. This comes out if you worked out using the calculator. This will be 0.998 whole square, subtract by 1, take the root, and then worked out. This comes out to be, which we have measured with calculator, this is 34.80 into 10 to the power minus 6 seconds. So the time which was in its frame was 2.26 10 to the minus 6. Here it is 34 from the relative to the observer in the rest frame, the earth frame. This is 34.8 10 to the minus 6 seconds. Now, according to us, this must decay in this much time, and it's moving with this velocity. You can measure the distance up to which the new meson must have traveled in this time. So you can take the time, the distance traveled. So the distance traveled by the new meson is equal to the time into velocity. So it is velocity into time, which is measured relative to the earth, and the velocity is 0.998 c, and the time is 34.80 into 10 to the power minus 6. This is the velocity, this meter per second, this is second. So this come out to be meter. So this is meter per second, and this is second component. So this comes out to be meter. If you multiply it, you will get 0.998. The speed of light is 3 into 10 to the power 8 meter per second. So and this is 34.8 into 10 to the power minus 6. This comes out to be about 10,419.856 meter. Simply multiply this by 3. Suppose this as 1, so it will be 3. Multiply 3 by 34, so you will get about 105, which is nearly 104. I use this 10 power minus 6 to 10 power 8 plus 2. So, and if you convert into kilometer, this will 10.419 kilometer. This distance is 10 kilometer. That's why we observe new meson at the surface of the earth at the sea level also. So this proves the verification, this experiment which is observed that new meson are observed at the surface of the earth, at the surface of the sea level also. It proves the verification, the time dilation, or it proves the Lorentz transformation. So, okay.